moderator, Muhammad Ghozali from Research Center for Chemistry, Fredina Destyorini from Research Center for Physics, Dr. Yu E. Xu from Department of Applied Chemistry, Osaka University, Japan, Dr. Andri Hardiansah from Research Center for Physics, and all super participants. Good afternoon and welcome to webinar on bio-based polymers and its applications. My name is Andi Suhandi from Research Center for Physics. I will guide this webinar as MC. This webinar is organized by Research Center for Physics, Indonesian Institute of Sciences, as part of our collaborations with Graduate School of Engineering, Osaka University, Japan. We apologize for the technical problems in the previous weeks that we failed to start the webinar earlier. Our agenda today, first, it will be started by opening remarks by Director of Research Center for Physics, followed by photo sessions. Next is the presentations and discussions guided by moderator as our main event. And last, the webinar will be closed by MC. Ladies and gentlemen, we would like to start our webinar with the opening remarks from Director of Research Center for Physics. Please welcome Dr. Rika Yudianti. Dr. Rika, time is yours.
Ya, terima kasih. Assalamualaikum warahmatullahi wabarakatuh. My respectful Dr. Su from Osaka University and Bapak Muhammad Ghozali from Research Center for Chemistry and Ibu Dina Destyorini from Research Center for Physics. And thank you very much for your willingness to join with in this seminar. And the audience, thank you to you all for to come to join with our webinar. And very happy today I can meet all of you in good health because we still face a global pandemic, COVID-19. So the number increasing number of infected persons still higher. So this webinar is virtually organized by Research Center for Physics by inviting our collaborator from Osaka University, Dr. Su, who same laboratory with Professor Hiroshi Uyama from Department of Applied Chemistry, Osaka University. In the last month, Dr. Su actually want to visit here in Indonesia, but unfortunately, COVID-19 just started in that time. So she has to postpone her visit to Indonesia. So maybe in near future, you can, Dr. Su can visit to Indonesia again. So in this webinar, Dr. Su will share to us about nanocomposite hydrogel for biomedical application maybe. And for this opportunity, this webinar, I also invited Bapak Muhammad Ghozali to share us about the starch-based bioplastic from its synthesis, recycling, and implementing to the society. And Ibu Fredina Destyorini as one of doctoral students in our research center who getting study in Professor Hiroshi Uyama laboratory, who will share us about the potential usage of biomass fiber, which producing carbonaceous materials for electrochemical devices. So in this webinar, we take up a topic about the biopolymers, holding a very important topic in for development science and technology, because the abundant resources and sustainable resources in the world. So the cheap price and sometimes the cheap price and potential usage in future application. So I think that's all for my talk today. Hopefully this seminar will open opportunity to get to share insight, experience, and future development of biopolymer usage. Again, thank you very much for all audience to join with us. And this seminar is meaningless without your participation. Last but not least, I say thankful to the committee, Pak Arif, Pak Andi, Pak Andri, and all members of Low Dimension Functional Material Research Group in our Research Center for Physics. Okay, thank you very much, and we hope this pandemic COVID-19 will end soon. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you, Dr. Rika Idanti, for the warm opening remarks, and safe journey to you for your evening schedule today. Okay, ladies and gentlemen, our second agenda is photo session. For the photo sessions, please turn on your video and have a big smile. Mr. Arif is our host. He will give a comment for every page you will take. Mr. Arif, time is yours.
Okay, ladies and gentlemen, it's time to photo session. Please, everybody to turn on your web camera. Okay, please. Okay, we start from the first page. Smile, 1, 2, 3. Okay, and then we go to second page. Please, everybody to turn on your web camera. Okay, 1, 2, 3. Okay, and then we go to third page. Please turn on your web camera. 1, 2, 3. Okay. Okay, thank you, ladies and gentlemen. I'm giving back to Pak Andi Suhandi. Please, Pak Andi. Thank you.
Thank you, Mr. Arif. Thank you, Pak Arif. Okay, ladies and gentlemen, we come to our main event, which is presentations and discussions by three respectable speakers, moderated by Dr. Andri Hardiansah. Please welcome Dr. Andri Hardiansah.
Yes.
Dr. Andri, time is yours.
Okay, thank you, Mr. Andi Sohandi, for the time. Okay, we will move to the main session for this event. And the first section will be delivered by Mr. Muhammad Ghozali. And I would like to introduce about the curriculum vitae. Mr. Muhammad Ghozali worked at the Research Center for Chemistry, Indonesian Institute of Sciences, and then his research mainly about the polymer chemistry, biopolymers, biodegradables, and bioplastics. And today, Mr. Muhammad Ghozali will share to us about the biodegradables polymer for packaging application. And I think that's all for the introduction. And Mr. Muhammad Ghozali, the time is yours.
Thank you, Mr. Andri, for your nice introduction. Stop share. I'm sorry, I will share my PPT. Bismillahirrahmanirrahim. Assalamualaikum. Is my slide visible, Mr. Andri?
Yes.
Okay.
Yes, please.
Yes. Okay, thank you. Good afternoon to Dr. Rika. From this picture, what's in your mind? river pollution, marine pollution, or microplastic. It's definitely environmental problems. And how to handle it? It can be handled into treatment. Curative and reducing or make a waste bank as known as bank sampah and waste management site TBS. Well, developing eco-friendly biodegradable polymer materials. And as a researcher, we have to do something to handle these environmental problems. In the last few years, we often hear and see some slogan like I am not plastic, and I am not biodegradable plastic, and I am Muhammad Ghozali, a researcher from Research Center for Chemistry. And before we get into biodegradable polymer for packaging application, let's understand the definition of biodegradable polymer first. And I will share our activities as a researcher and a citizen. Based on the definition of European Bioplastic Association, bioplastic is a plastic that is bio-based and or biodegradable. And biodegradable plastic is a plastic which can be completely biodegraded through biological activity, such as the of microorganisms as bacteria. Under aerobic condition, the resulting products should be biomass, carbon dioxide, and water. And under anaerobic condition, the resulting product should be biomass, carbon dioxide, methane, and water. While a bio-based plastic is a plastic that is wholly or partly derived from biomass. And the oxo-biodegradable plastic is a plastic that has additive included to accelerate its fragmentation by heat or UV radiation. And the last, degradable plastic, it implies that the plastic breaks down, but does not give information about the end of product or method of degradation. By further degradation, or and this is the classification based on the source of raw materials and biodegradability. You can see here the bioplastic. If we say bioplastic, it is a plastic made from biomass. It can be biodegradable or non-biodegradable. For example, bio-PET, bio-PE, and bio-PP are bioplastic. They are renewable, but non. Well, that-based bioplastic is a bioplastic and biodegradable. Well, if we say biodegradable, it can source PCl and PPET are biodegradable polymers that come from non-renewable resources, from petroleum derivative. Activity are in develop product based on biodegradable polymer materials such as cellulose, and then starch, PLA, and chitosan. This time I will focus on starch because starch is a zero waste product from industry. As we know, tapioca starch can be obtained from cassava without chemicals by extraction process, and the extraction process to waste. There are liquid waste tapioca and solid waste tapioca. Liquid tapioca waste can be converted into bacterial cellulose and used as a biodegradable bioplastic, while solid tapioca waste can be converted into biofoam and non-wood paper. The first our product is biodegradable plastics. This is extruder in our lab. In the extruder, we mix starch with several additives such as plasticizer and compatibilizer or others to produce biodegradable bioplastic pellet. And the resulting pellets then blow using blow machine to produce biodegradable bioplastic bags for further application. In addition, we also develop several products from PLA, cellulose acetate, chitosan, starch, and also, like I said before, bacterial cellulose. We synthesis bacterial cellulose from liquid tapioca waste, and based on the result of FTIR, SRD, and SEM, the synthesis of bacterial cellulose has been successfully conducted, and it is on same showed that the bacterial cellulose structure was arranged of rod-shaped nanofiber that form a fine and dense network and arranged randomly and without pattern. It is on the 3D network-like structure, and this bacterial cellulose can be used as reinforced agent for the bioplastic, and this is the bioplastic pellet that's reinforced by bacterial cellulose, and the liquid tapioca waste could be used as a cheap and potential medium for bacterial cellulose production. And the next our product is biofoam. We process solid tapioca waste into biofoam and add color additive to make it more attractive. This biofoam, if in the soil or compost environment, can be decomposed naturally for 2 weeks. Let's see in the video. In a week, it will be crushed into small pieces, And then in 2 weeks, it will be decomposed naturally. And we also working with partner in Ministry of Agriculture to develop biofoam that is resistant to hot water. This hot water from a dispenser, and you can see the water vapor here. And this biofoam also washable. After washed and dried, you can reuse again. You can reuse this biofoam again. I think this biofoam has potential for instant noodles or hot tea. And the last our bottom, the solid tapioca waste, and we also can adjust the flexibility of non-paper. You want rigid or flexible, and you can write in the non-wood paper. The paper also can laminate it like this picture and the non-wood paper. We also try make a non-wood paper cup. It's not perfect, but I think it's okay for a sample. You can see in this video, this is very, very flexible non-wood paper. And this is the rigid non-wood product. We hope that in producing paper, there is no need to deforestation anymore. And as a human, we can also help to handle waste through waste bank or bank sampah and waste management set, TPS. We can sort the waste by type and the non-organic waste or organic waste, and the organic waste can be converted into biogas and feed and plant media. And this is our activities at home. We sort the waste and we try to make eco brick from multi-layer packaging containing aluminum. And we also receive waste from resident, from our neighbor. And this is the stove and lamp. Use biogas as a fuel. And this is the last slide. This is our team. Dr. Wita, Bu Evi, Bu Mia, Bu Yeni Meliana, and Pak Agus Saryono. And this is you will find our effort and activities to handle environmental problems in my channel. And thank you, Pak Andri.
Okay. Yeah, an excellent presentation. I think especially for packaging application, and lots of results have been done with that. And for the audience, if you have any question, you can type on the chat, and we will also have a discussion after the all of the presenter present the presentation. And I think we will move to it will be delivered by Ms. Fredina Destyorini. Before start presentation, I would like to introduce Mr. To be used for electrochemicals application. And right now, she's a GSP Ethron Paku dissertation PhD fellow at Osaka University for fiscal year 2019 and 2021. And current research about the fabrication of graphite carbon paper from coconut coir for gas diffusion layer of PM fuel cells. So I think Ms. Fredina is already ready for presentation. Ms. Fredina.
Thank you, Dr. Andri Hardiansyah.
Yes.
If you see slide on your okay.
Yes.
Good
You can start
afternoon.
your presentation.
Okay. Thank you, Dr. Andri. Good afternoon, everybody. My name is Fredina Destyorini, a researcher from Research Center for Physics, LIPI. Today, I will give a review about utilization of biomass waste as renewable carbon source and its potential application in electrochemical devices. Okay, let's start. This is the outline today. Consists of introduction, fabrication of biomass-derived porous graphite carbon, or we will call it with BPGCs. In this section, I will talk about activation process, catalytic graphitization, and also the combination method between catalytic graphitization and chemical activation. And the next section, we will talk about the application of the BPGCs, especially as a material for fuel cell, lithium-ion battery, and supercapacitor. Okay, as introduction, it is generally known that global energy consumption is dramatically increasing due to higher standard of living and the increasing of world population. Most of our energy comes from fossil fuel, and burning this fuel causes environmental pollution. And we know that fossil fuel is a non-renewable resource, so it has a tendency of availability, depleted, and exhausted. Therefore, this global problem, the depletion of fossil energy, environmental pollution, global warming, and also waste disposal have become the focus of the international community. In the face of its increasingly severe global energy and environmental problem, the development and utilization of new and renewable energy sources have become the common choice for countries around the world to ensure energy security and achieve sustainable development. Electrochemical energy devices is one option of this new and renewable energy source. Among them, fuel cell, lithium-ion battery, and supercapacitor are the most typical and popular electrochemical energy conversion and storage device. And carbon material have been the ideal candidate material for this electrochemical energy device because of their diverse structure, rich surface area, strong controllability, and good chemical stability. Porous carbon material with a high surface area and good stability have been widely used as electrode material for supercapacitor, lithium-ion battery, and fuel cell. And the use of biomass waste as carbon precursor also is a great approach in waste management and pollution control strategy. Following advantages of biomass waste as a carbon precursor, they are highly porous structure, abundant, and renewable. However, generally, biomass-based carbon material with a conventional treatment, in this case with a pyrolysis method only, have the following disadvantages. They are poor graphitic structure and low degree of graphitization that are not conducive to the transmission of ion and electron. This problem have limited their further application in the field of energy conversion and storage. So, to overcome this problem, several researchers have developed BPGCs. With their unique characteristic, BPGCs have attracted great interest for electrochemical energy devices. At present, the preparation of BPGCs can be divided into 4 main methods. They are pyrolysis, chemical activation, chemical graphitization, and the combination of catalytic graphitization and chemical activation method. As we know, pyrolysis is as the general method to convert biomass into carbon material due to the heat treatment under inert condition. Carbon material is obtained by the degradation process of lignocellulose compound like hemicellulose, cellulose, and lignin at different temperature. For the remaining 3 methods, I will discuss more detail in the next section. So, with this 3 main method, we can obtain carbon material from various biomass waste with a unique characteristic, porous structure, and graphitic structure. BPGCs, carbon material from biomass waste, with high porous structure and graphitic structure is suitable for electrochemical energy device like supercapacitor, battery, and fuel cell. Some researchers also use this material for environmental protection, like absorber material, but it is not our focus now. And next, we go to fabrication of the biomass-derived porous graphitic carbon. First method is chemical activation. Chemical activation has purpose to further improve the porous structure and increase the specific surface area of carbon. The chemical activation method is usually mixing the activator and biomass material in certain proportion, followed by slow pyrolysis under the protection of an inert atmosphere. The common activator are like potassium hydroxide or KOH, phosphoric acid, zinc chloride, and also potassium carbonate. And among them, KOH is the most popular chemical activator that generally used. Activation mechanism of KOH on carbon consists of several simultaneous reactions, like this following reaction. Start from the dehydration of KOH to transform into potassium oxide at 400 degrees Celsius, and then carbon is consumed by the reaction of carbon and H2O with the emission of hydrogen gas, and potassium carbonate is formed by the reaction of potassium oxide and CO2. And then as from potassium carbonate significantly decomposing into CO2 and potassium oxide at temperature higher than 700 degrees Celsius and completely disappear at 800 degrees Celsius. Moreover, the resulting CO2 can be further reduced by carbon to form CO at high temperature. And the key compound or potassium compound like potassium oxide and potassium carbonate also can be reduced by carbon to produce metallic K at temperature over 700 degrees Celsius. So there are So there are three main conclusions about the activation mechanism of QOH on carbon, which have been widely accepted. The first is chemical action, physical action, and then carbon lattice expansion. Okay, this is some paper that report about chemical activation on biomass-waste. Zubrick et al. Reported the synthesis of activated carbon from corn stalk by chemical activation through two methods, single stage and two-stage pyrolysis process. The single stage synthesis was realized to use one time of pyrolysis process, while two-stage was performed by 2 times of pyrolysis process to produce activated carbon. For a single stage process, the granular powder of cornstalk was mixed with QH solution, followed by pyrolysis process in nitrogen atmosphere at 550 degrees Celsius. And after washing this product, they obtain A1 sample. Well, for the two-stage pyrolysis process, the granular powder of cornstalk was firstly pyrolyzed in nitrogen atmosphere at 550 degrees Celsius. After that, the obtained char was impregnated with QH solution, followed by second pyrolysis process at same temperature. After washing this, the sample A2 was obtained. This both method produce an activated carbon with different porous character. The sample after the single stage process was more homogeneous and well structured, while the two-stage pyrolysis caused cracking of network and creating of heterogeneous particle with a quite irregular structure with opening of pore and on the structure on the surface. This phenomenon was caused by pre-carbonization step before the chemical modification. Thus, the chemical agent can react differently with carbon char as it was in the single state process. Activated carbon prepared by two-stage pyrolysis saw better porous development related to high porosity, surface area, and that parameter related with much better absorption properties compared to the single process. And the next is evac other parameter in chemical activation process. Zhang et al. Reported the chemical activation process on garlic skin using QOH as activator agent. They investigated the effect of alkali carbon ratio, activation temperature, activation time, carbonization temperature, and also carbonization time on the specific surface area and pore volume. This is the method to obtain the activated carbon. So the garlic skin powder was pre-carbonized first under nitrogen at various temperature and then mixed with QOH and then heat treated with a pure nitrogen at the various temperature. The chemical activation process conducted with these various conditions. This is, you can see this various condition. And using that there are parameters affected on the surface area and pore volume of carbon. There are effect of impregnation ratio. With the ratio increase, more carbon can react with the activator, generating more pores, and eventually increase the specific surface area and the pore volume. When the ratio exceeds the optimum point, excess QOH react with the carbon atom, causing the excessive ablation of the carbon. The carbon skeleton around some micropore collapse, making some micropore combine to form mesopore or even macropore, leading to the decrease of the specific surface area and pore volume of carbon. While for the activation temperature effect, initially, as the temperature increase, more energy is provided for the reaction and more carbon atoms at the active site are consumed to form pore, which makes the specific surface area and the pore volume gradually increase. However, when the temperature further increased, the diffusion rate of potassium ion increased, accelerating the reaction rate of carbon atom at the active site, ablating the foam micropore and collapse of the carbon skeleton. And it led to decrease of the specific surface area and the pore volume. And the activation time, we can see that the specific surface area and the pore volume almost linearly increase with the activation time, which may be attributed to the increased pore volume from the activated carbon atom and the activator in the longer reaction time. And effect of carbonization temperature, the specific surface area increased with carbonization temperature and reach the maximum value, after which it starts to decrease. And the last is the effect of carbonization time. The specific surface area and the pore volume fluctuated in small range, indicating the least effect of carbonization time. And this is the optimal condition to synthesize the activated carbon from garlic skin. And in general, the influence level of preparation condition on the pore structure of carbon followed this order. The carbonization temperature is the highest, give the highest effect, followed by activation temperature, the impregnation ratio, the activation temperature, and the last is the carbonization time. Okay, in this slide is just a summary of various biomass-derived carbon material by different activation method. Many biomass waste were proved to utilize as activated carbon with high porous and surface area using activation process. And next is the catalytic graphitization method. During chemical activation, the porous structure of biomass can be typically developed, but the graphitic structure is ordinarily not perfect, causing the relatively low electrical conductivity and limit its application. So it is needful to improve its graphitic structure to enhance the electrical conductivity. Generally speaking, to convert the hard carbon structure formed in the pyrolysis process biomass into an ideal graphitic structure without catalyst needs super high pyrolysis temperature up to about degrees Celsius. Super high temperature condition consume a lot of energy and costing. But catalytic graphitization proven to graphitize of carbon and increase its electrical conductivity at lower temperature by introducing catalyst into amorphous carbon. Graphitization catalyst cut the activation energy of transition from amorphous to graphite phase, so that graphitic carbon is obtained at lower temperature. Generally, catalytic graphitization is conducted by impregnating the catalyst like iron, cobalt, nickel, and their oxide, and carbon material in certain proportion, followed by pyrolysis under protection of inert atmosphere. At present, there are two mechanisms of catalytic graphitization. The first one is dissolution and reprecipitation mechanism, and the second is the carbide transformation and decomposition mechanism. For the dissolution and reprecipitation mechanism, under the action of graphitization catalyst, the chemical bond between the carbon atom are broken, and then the catalyst continuously dissolve the amorphous carbon until it reaches saturation. The energy level of saturated carbon is higher, so it needs to be converted to low-level graphite crystal state, thereby obtaining a graphitic carbon material. And in carbide transformation and decomposition mechanism, the graphitization catalyst first combine with the carbon material to form a carbide and then decompose to form graphitic carbon. But it should be pointed out that above two mechanisms are relatively clear about the catalytic graphitization, and the mechanism of catalytic graphitization of biomass is very complex, and there are still many to be explored. Okay, this is our research about the catalytic graphitization. We obtained the graphitic carbon from coconut coir or coconut fiber. This is the root of our experiment. First carbonize the coconut fiber at 500 degrees Celsius and then impregnate it with the nickel-based catalyst and graphitization process at relatively low temperature at 1,300 degrees Celsius. And after the acid treatment, we can obtain the graphitic carbon. Okay, from the XRD sample treated with nickel, this one, this is before acid treatment and this is after acid treatment, contain a strong peak center at approximately 26.5 degree. This diffraction peak corresponds to the 002 plane of graphite, and it was also observed in the XRD pattern of commercial graphite. We also compare with the commercial graphite. In contrast, the pattern of the sample that underwent heat treatment at the same temperature without the nickel catalyst, this one, contained a broad peak that was shifted in the negative direction. This indicates that the sample contained large amount of disordered carbon or an amorphous phase. This result show that the nickel particle could catalyze the graphitization of coconut coir at a pyrolysis temperature as low as 1,300 degrees Celsius. The DEM image of sample without catalyst was typically of an amorphous carbon material. The diffuse halo in the side pattern confirmed that the carbon without catalyst sample was an amorphous phase, while for the nickel treated sample indicate the presence of graphitic structure obtained the same temperature with catalyst. In the low magnification time image of the sample, the nickel treated sample, so spherical projection with nickel nanoparticle in their core. And in the high resolution TM image shows cell around the nickel nanoparticle with well-defined lattice fringe, and the graphitic layer were separated by an interplanar distance of about 0.3367 nanometer. It's closer to the lattice spacing of commercial graphite powder. Okay, next, the last mechanism is combination between activation and catalytic graphitization. As I mentioned in previous slide, that the carbon structure from biomass obtained by chemical activation only has a good porous structure but low content graphitic structure, and it limits its application in electrochemical field because the structure will not conducive to the transmission of ion and electron, while catalytic graphitization only, with catalytic graphitization only that conducted on biomass-based carbon produce a good graphitic structure, but low porosity and surface area. The structure also provides unfavorable condition in the electrochemical application because it is not conducive for ion storage and gas diffusion. From the previous discussion, it can be known that the promotion of the graphitization degree caused by the graphitization catalyst is able to balance the reduction of the graphitization degree caused by activation agent. Accordingly, the combination of chemical activation and catalytic graphitization is a promising pattern of preparing BPGCs. This is the method. The activator agent like potassium oxide and etc. are used to stimulate and develop the porous structure, and the catalyst agent like iron, cobalt, and nickel is used to catalyze the formation of the graphitic structure. This combination method could produce the carbon material that have good porous structure and high graphitic structure as well. Okay, this is the example of activation and catalytic graphitization method. They use coconut shell as carbon source, zinc chloride as activator agent, and iron trichloride as graphitization catalyst. In a typical synthesis, coconut shell was mixed with zinc chloride in ferric trichloride solution, and the activation and graphitization process of the carbon precursor was carried out at 700 to 1000 degrees Celsius. This figure is XRD pattern of the carbonized sample before acid treatment, and the PGNS is after acid treatment. Before acid treatment, the diffraction peak at 26.5 degree can be assigned as the 002 reflection of graphite, and two sharp peak at 44 and 65 degree are indexed to the iron component. After washing with acid solution, the iron component can be removed. The XRD pattern of resulting after acid treatment sample show a sharp and narrow of 002 diffraction peak, implying the high crystallinity of sample after acid treatment. The graphitic characteristic of PGNS, or a sample after acid treatment, is further confirmed by Raman spectroscopy. This is show the higher G band compared to D band, and presence of 2 D band. The increase of the carbonization temperature can result in an obvious improvement in crystallinity. Moreover, the BET surface area of PGNS sample show the high surface area of all sample is about 1,200 to 1,800 meter square per gram. Okay, next slide is about energy application of BPGCs. First, we talk about fuel cell application. Fuel cell is type of environment-friendly electrochemical energy conversion device that can directly convert chemical energy into electric energy on the basis of redox reaction without the combustion process. The oxidation of fuel, in this case, is hydrogen oxidation, occur at the anode, and the oxygen reduction or reaction or ORR at the cathode. A PEM fuel cell poses a multi-layer architecture and typically consists of anode and cathode, flow, and a membrane electron assembly like this illustrated in this figure. Several papers reported the application of biomass-based carbon as catalyst layer and gas diffusion layer due to its porous structure, low cost, and relatively easy preparation. Gas diffusion layer perform the following essential function to transport of electricity, reactant gas, and heat, as well as the providing structural support to the assembly. GDL is typically porous carbon-based product, including woven carbon cloth and non-woven carbon paper, while the catalyst layer is thin layer where electrochemical reaction take place. The electrodes are usually made of porous mixture of nanoparticle dispersed on porous carbon material and ionomer. And biomass carbon has a potential to utilize as gas diffusion layer, replacing the commercial carbon paper due to its porous and conductive. Biomass-derived carbon material also have begun to be studied as non-precious metal catalyst for the ORR, replacing the PTC catalyst. Okay, this is some paper about the utilization of biomass waste as ORR material, ORR catalyst. The biomass material are usually required to be pre-treated and converted to catalytic composite to fulfill the fundamental requirement for electrochemical ORR. The material for electrochemical ORR should have well-defined active site, high chemical and electrochemical stability, and also superior electric conductivity. One method that is well known to synthesize catalyst material for ORR is a single transition metal nitrogen dope carbon catalyst, or we call it with MNC catalyst. And biomass-derived transition metal nitrogen dope carbon material have been considered to be promising ORR catalysts. And in this paper, we had all obtained heteroatom dope carbon, CO, KCM, by directly carbonizing kelp pre-impregnated with cobalt. We can see from the TEM indicate that CO cobalt nanoparticles are uniformly dispersed in the sample. With higher magnification, we can see that surface of CO nanoparticle were encapsulated by multilayer graphene. During annealing at high temperature, cobalt acts as catalyst to facilitate the graphitization of carbon around them and form this core cell structure. XPS data reveal the presence of CO and CO. Okay, from the LSV testing, from the ZV in 0.1 molar QH was confirmed that as synthesized product has the characteristic of electrocatalytic sensitivity for ORR under alkaline environment. Okay, this is application of biomass for GDL. This is our research also. We successfully produce the GDL from coconut fiber at temperature 1,300 degrees Celsius. And we also successful to test this composite in the single cell of fuel cell and its function performance compared to the commercial carbon paper. And for lithium-ion battery, the critical requirement for anode material of lithium-ion battery is it should be higher specific surface area, hierarchical porous nanostructure, and higher degree of graphitization and nitrogen doping. I will talk faster because the time is limit. And the biomass-derived carbon material BPGCs as anode material due to the extensive resource, low cost, and stable electrochemical performance. Okay, this is paper about the biomass application in the battery. From the wet stock with the calcination and graphitization method at higher temperature, we can see that it has a good performance in as a battery or as an anode of lithium battery because the synergistic effect of the high graphitization degree, graphene-like structure and porous structure, and it causes greatly facilitate diffusion, intercalation, and deintercalation of lithium-ion and rapid electron transfer. And for supercapacitor, biomass apply as supercapacitor because the good porous surface area, electric conductive, and also low cost. But the material as electrode material of supercapacitor have to have reasonable porous structure and high surface area, have an excellent electrical conductivity, and also widely available and low cost. And this is the example of research about the application of BPGCs as supercapacitor. We can see from spruce bark, tubular cellulose fiber, we can see that it's show the good performance and stability of the supercapacitor. Okay, this is our activity in our lab. We are focused on the productivity, produce graphite carbon from biomass like coconut coir, oil palm fiber, and coffee waste, and so on. Maybe it's enough. Dr. Andri?
Okay, Ms. Fredina, thank you for your nice talk about the biomass transformation by using catalytic graphitization, and we learned a lot about the process. And for the audience that might have a question, please write your question in the chat box. Okay, thank you, Ms. Fredina, for the presentation.
You're welcome.
And we will move to the last presenter for today, Dr. Su.
Okay. Wait a minute. Maybe I have to share my presentation.
Yes. Okay. Okay. Before Dr. Su start the presentation, I would like to introduce about the CV of Dr. Su. Dr. Su is one of the staff in the Department of Applied Chemistry, Graduate School of Engineering, and her education, PhD in Engineering, Department of Bio-based Material Science, Kyoto Institute of Technology, Kyoto, Japan, 2015. And right now, she's assistant professor at Osaka University, Osaka, Japan, and some research fellowships in project researchers in Department of Biomedical Engineering, and postdoctoral researchers in Department of Biomedical Engineering, Research Institute, National Cerebral and Cardiovascular Centers, Osaka, Japan. Okay, that's the introduction for Dr. Su. And Dr. Su, time is yours for sharing your research.
Okay, thank you. Can you hear me clearly? Okay.
Yes.
So, thank you. So today, I'm very happy I can share my work in this webinar. And actually, I'm a little confused to what I can say today. And because as the introduction, before before working in the Department of Applied Chemistry, I worked at the NCVC, National Cerebral and Cardiac Center. It's a hospital and research institute. And so actually before I work about like using the bio-based polymer to make some like the biomaterials. So today I want to introduce another field of the bio-based polymer. So it's my work previous, and now it's also another a student is work as the using the develops a novel stimulus responsive hydrogel based on the bio-based polymer, especially is biodegradable. So it's already introduced, so I will pass this page. So injectable scaffold material for tissue regeneration is have to, you can use a kind of the hydrogel has a stimulus responsive. So this kind of the stimulus responsive hydrogel can have the chemical or stimuli or the modulus biosignal or the biofabrication technology to make this kind of the hydrogel. So actually to applicate in the human body, maybe have the ionic interaction or the hydrogen bond. And also some paper is have the temperature responsive and the photopolymerization or the, so especially today I want to introduce one part of the hydrogel is based on the enzyme reaction. So using this kind of the hydrogel, we can make a kind of the hydrogel mixed with the stem cells or protein or the growth factor, and then make one kind a kind of the 3D tissue scaffold to test the cell to grow into the hydrogel. However, that have many kind of the tissue in the human body, like the bone or the cardiac or muscle, and different tissue has the different elastic modulus. Like the fat is very soft, and bone has a high elastic modulus. So we have to control the hydrogel elastic modulus of the hydrogel to make the different hydrogel. So stimulus response hydrogel, especially the bioabsorbable hydrogel, it can be used as developed as a cell transplant matrix. So using this kind of the hydrogel, we can mix with the polymer solution with the cell and inject into the tissue deficient part. And then the cell scaffold will formate by the temperature or the enzyme or photo reaction or something. And then the cell can be growth on the scaffold. So after, because this is a bioabsorbable, so after during the tissue regeneration, the scaffold can also be degraded after the tissue regeneration. So this kind of the material we can use to fix the tissues without surgical operation. However, as I said before, the cell because have the different type of the tissue in the body, so the hydrogel strength and the gelation time is very important to design this kind of the stimulus responsive hydrogel. So today I want to introduce two part of the hydrogel. Is based on the we know that the bio-based polymer is like the polylactic acid polylactide, PLA, and also another part where I will introduce another part is about the polyglutamic acid. So this kind so we know that PLA is based on the corn, and it's biodegradable and biocompatible and non-toxic. So, but because PLA is hydrophobic, so it's different to make one kind of the hydrogel. So after I will introduce how to make this hydrophobic PLA to the hydrogel. And the PGA is, like this photo, you can see this is a special food in Japan, is natto. So PGA is one kind of the polymer we can take the PGA from the natto. It's like this kind of the line. So it's biodegradable and biocompatible, non-toxic, and also it's a water retention and it's thickening. So this kind of the bio-based polymer is actually very good for hydrogel. And the second part I want to introduce this kind of the hydrogel with the enzymatic cross-linking. So first is about the PLA hydrogel. So we know that the hydrogel, the PLA is a carbon neutralized polymer. And also it's very important that actually PLA have two kind of the enantiomer polymer. Is like the L-lactic acid and the D-lactic acid. So these two kind of the PLA and PDLA is the revised helix. So after they mix together, it will be combine together and form the cell complex like this one. So, so as I mentioned before, that PLA is a hydrophobic. So how we can make this hydrophobic polymer to the hydrogel? So first, we have to synthesize a copolymer with a hydrophilic segment. So in this study, we use the polyethylene glycol, the PEG, and synthesize a copolymer, amphiphilic copolymer. And we can disperse the copolymer into the water. So you can see at here, the core will be the hydrophobic PLA, and at the shell, it will have the hydrophilic PEG. And dibrocopolymer of the PLA and PEG, it will be formed to the corona micelle. And about the tricopolymer, we can form the flower micelle, flower type of micelle to exit this figure. And also because PLA has the enantiomer, so we can mix the PLA and PDLA to form the cell complex as the cross-linker of the micelle. So as you can see at here, after we mix the PEG PLLA micelle and the PEG PDLA micelle, actually after heating, the cell complex will be formed, and then the micelle and micelle will be linked together as a cell complex as a cross-linkers. So using this kind of system, we can develop a thermosensitive bioabsorbable hydrogel, so that we can inject to the we can make the solutions, micelle solution, and then inject to the body, and it will be form the hydrogel in the body. So based on this idea, because corona micelle and the flower type of micelle will be very different. Actually, it has the different sol gel transition and gel source transition. I will mention after. So using this kind of the micelle, actually we can mix the corona type micelle and the flower type of micelle, so to make the new sunflower type micelle, and then have the gelation. And then we also introduce this elder reaction to make more cross-linker between the micelle. So in this experiment concept, we want to first is control the dibroc and tribroc ratio to control the gelation times, and then after gelation, after control the gelation times, and also we can introduce another reaction to the hydrophilic segment to increase the gel strength. So first, I want to introduce how we can we can control the dibroc and tribroc copolymer ratios. So first, because after we want to have the del cell reaction in the hydrophilic segment, so first we synthesize the phosphorylation group to the PEG end to have to obtain the dibroc copolymers. So you can see that like here. So this is the phosphoryl PEG PLA and PLLA PEG PLL micelle solution. So we can earn this, we can obtain this kind of the sunflower type solution micelle. And as I mentioned, because actually dibroc copolymer, only dibroc copolymer, if the strength, the hydrogel strength will be very high, but it will become hydrogel at a low temperature. So we cannot inject the dibroc, only the dibroc copolymer micelle solution to the body, because first it already becomes a hydrogel. But about the trichlorocopolymers. The trichlorocopolymers might show actually it can be have a very good salt to solution to gelation transition during the temperature rising. So we can prepare one. We can prepare the solution at a low temperature, and then we can rise the temperatures to earn the hydrogel at the body temperatures. And also because in this figure you can see that if the diprocopolymer ratio is too high, the sunflower type micelle will become the hydrogel at a low temperature. So this time, so when the diprocopolymer ratio over 80, it's very difficult to applicate for the injectable hydrogel. Also, we can in this slide we can control the storage modulus and the gelation times and the gelation temperature with the ratio of the diprocopolymer and the trichlorocopolymers. So you can see that here the storage modulus increase with the increasing the diprocopolymer ratio. So it's very easy to we can only control the diprocopolymer ratio and then get the very from 500 to 3,500 Pascal still modulus. So have a very wide range of the storage modulus. Only controls the ratio of diprocopolymer. And also after we also the gelation times and the gelation temperature will decrease with the increase the diprocopolymer ratio. So we can by controlling the ratio of diprocopolymer and trichlorocopolymers, the salt to gel behavior shows as here, and also the electron modulus of the gel and the gelation times and the gelation temperature can be controlled. So because as I mentioned before, applicate in the tissue regenerate, so this kind of the different modulus, and also we can control the gelation times. So it's very important for design for the tissue tissue regeneration. So because we introduce a porphyryl group to the hydrophilic segment, so we also can add a bismuth compound, and then to increase the gelation, increase the cross-linker of the hydrophilic segment, so to improve the gel strength. So you can see at here, if we only measure the electric modulus of the PLLA, only PLLA micelle solution, you can see that this, because it's a solution, so it's the storage modulus is not very stable because it is the solution. And also, if we add the bismuth compound to the solution, actually it cannot be increased very much. But if we add the bismuth compound to the DL mix micelle solution, you can see that before add the bismuth compound is around the storage modulus is around 4,000, and after the delta reaction, the compound can be the storage modulus can be increased to 2 to 3/4 of the micro solutions. So also, so we can, here is also we add another kind of the, we control, here we also control the molecular weight of the dibrocopolymer and tribocopolymer, and also the dibrocopolymer ratios. So all of the micro solution can be the storage modulus of the micro solution can be increased after we add the bismuth compound. So in this slide, we can show that the Destyorini reaction increases the cross-link of the hydrophilic segment and increase the gel strength. So this is the conclusion about this work. And so as you can see here is a TEM result. So first we mix the dibrocopolymer and tribrocolpolymers, and then make a sunflower type micelles. So you can see that it's the sunflower type micelle. And also after the gelation by the after we mix the PLA and PDLA sunflower type micelle, so you can see that it can be gelation by the cell complex, and the TEM result is also shows that the micelle is linked with together. The micelle is linked to each other. And then after the Destyorini reaction, actually is only the link with the hydrophilic segment. So you can see that as the TEM result, is the micelle can be linked together to form the very big network in the hydrogel. So so in this study, so first is I want to say that it's very easy to control the gelation time and the gelation temperature by control the dibrocopolymer and tribrocopolymer ratios. And also we can increase the strength of the gel by introduce the Destyorini reaction. So the second part is about the PGA hydrogel, but I think the time is low, so I will just introduce very fast. So PGA is a very good material for cosmetic and medicine, and also food and some health supplement. And so how to cross-link this PGA, we want to introduce a novel reaction into the PGA network is the enzymatic reaction. So this kind of the enzymatic reaction actually is a phenol reaction, a reaction between the phenol. So the phenol-rich polymer, we can using this kind of the enzyme. So it's HRP and the H2O2 to link the phenol like this. So it's very good to, because this enzyme is also can be used into the body, so it's non-toxic. And but this kind of the network have one question, is that the mechanical property is very poor. So in this, So in this, so in this study, we want to increase the also those gel strengths to using the Destyorini reaction. So this Destyorini reaction is also used before, and so using this kind. However, Destyorini reaction has a problem that because the gelation time is very long, and also it cannot be injectable. Yes. So because the previous work we just increase the gel strength using the DA reaction, but the gel temperature and gelation time is controlled by the diblock and triblock copolymers. So to fix this kind of the so in this work to fix this kind of the problem, we use these two kind of the cross-linker to make the PGA network. So it's the enzymatic reaction and the Destyorini reaction. Oh, why is I don't know why this will be. Sorry. So in this slide, you can see that actually we can also be control the gelation times by changing the concentration of H2O2 and the HRP. So if we increase the HRP concentration, the gelation time will be decreased. And also after this line is the reaction that after we add the Destyorini reaction. So also it can be see that the after increase the Destyorini reaction, actually the store modulus of the hydrogel will be increased. And we can see that two kind of the network will be introduced to the hydrogel. So if we see the SEM structure, it will be the pore will be if we increase the cross-linker between in the hydrogel, the pore size will be decreased. So okay, this is also about the storage modulus. If only using the enzyme, actually the storage modulus is very low. And using the Destyorini reaction, we can increase the storage modulus of the hydrogel. So. And also this one is very important that because only enzyme, maybe the hydrogel will be very weak. So during the compress test, it will be broken. But if we introduce the Destyorini reaction, so you can see that the hydrogel will be very strong. So during the compress, it will be not broken. And also we can keep the shape of the hydrogel. So, okay, this is about we can control. It's also that we can control the stress of the hydrogel by the enzyme, the concentration of the enzyme. And so using this kind of the hydrogel, you can see that we can using this kind of the double syringe of the to inject this kind of the hydrogel. So this is only the DA and enzyme PGA, and the other syringe is the HRP and H2O2. So during this kind of the injection, actually the HRP and the PGA will mix together and become the hydrogel very fast. So we can also write this kind of the smooth letter O and U very successful. So this using these two kind of the cross-linker. So first, because the enzymatic reaction is very fast, so we can first fast to gelation the hydrogel by the enzyme. And then because the reaction will take time, so after injection, actually the hydrogel can be formed more strongly after maybe 1 hour to 2 hours. So now we are trying to measure this hydrogels increase the degradation times, and also we test the protein release. The protein could be released from this hydrogel and in a controlled way. So at the final, this is the Uyama laboratory. So we have many students in this laboratory. And the second part of work is studied by this student Wei-san. And also actually in the Uyama laboratory, we do many kind of the biomass plastic, bio-based plastic, or the hydrogel and the pore structure called monoliths. So this kind of, and now I want to study the hydrogel for the biomaterials. So maybe this will be a new research in the Uyama laboratory. Okay, thank you for your attention.
Okay, thank you, Dr. Su, for a very nice presentation, nice topic, and I believe we learned a lot about the hydrogels, especially novel stimuli hydrogels. And thank you again for joining us with this webinar. And okay, now we will have a question and answer sessions that I will get for some question that write on the chat box. Maybe I will read and then hope Mr. Ghozali, Ms. Fredina, and Dr. Su to answer the question. And for the first question, for Mr. Ghozali, is there any? Oh, this is from Vini Alvia from Gajah Mada University, major in chemistry, and the question is about how about is the material strength, such as modulus Young or tensile. And does the material considered safe when it is really introduced with extreme condition of food or beverage, hot or cold temperatures? And is there any difficulty when producing the product from its raw material? Thank you. Maybe Mr. Ghozali could answer the question.
Okay. Thank you, Mr. Andre, and I try to answer the question. And for the first question in the chat, until now, we can find someone or collector who handle the textile material. Our collector accept all non-organic waste, included styrofoam and single plastic use, but they didn't accept goods from fabric. So it's still our problem until now. And I said this time I will focus on tapioca start from cassava. Why? Because the waste from start production, we can use it for the other products. And start extraction can be done by peeling the peel of cassava and then chopping it and into small piece and mix it with water, and then filter it with pressure. And after filtered, you will get the starch with gravity, with the settle of gravity. And we also use tapioca waste from the tapioca industry. And we use glycerol as a plasticizer, and to overcome the mechanical properties of bioplastic starch, we reinforce it with cellulose. As we know, starch-based material has disadvantages related to hydrophilicity and low mechanical properties. And in general, until now, biodegradable packaging has been designed as a secondary packaging. So further research and testing is needed if used as a primary packaging that contact with food or beverage. And the last question, yes, both of them and any other problems. And until now, bioplastic have not been able to completely replace conventional plastic because their mechanical properties are still low when compared with conventional plastic, and also when we using natural material source, the uniformity of the raw material is still problems. And other problem related the price of bioplastics still higher compared conventional plastic. I think that's all, Mr. Andri. Thank you.
Okay. Okay. Thank you for the answer, Mr. Ghozali. I believe we understand the answers, and it's really comprehensive answers to related to bioplastics and its mechanical properties, and also the possibility to replace the conventional plastics. Okay, thank you, Mr. Ghozali. And the next question for Ms. Fredina Destyorini. And two questions related to the topics. The first one is, which one better, porous gravity carbons and hard carbon as anode in battery application? And the second question, why the graphitization without catalyst needs pyrolysis about 2 until 3,000 degrees Celsius, while without catalyst just below 1,400 degrees Celsius to become graphitic carbons? How does the affect? Ms. Fredina, please, the explanation.
Thank you, Dr. Andi and Dr. Andri, and the question. For the first question, as I mentioned in my presentation, that for anode material in lithium-ion battery application, there are critical requirements. Higher specific surface area and porous structure of carbon, and also higher degree of graphitization. Surface area and porous is need to provide more active site for the intercalation and the intercalation process of lithium ion. And higher degree of graphitization is need to further improve the electrochemical activity, defect, and conductivity of the material. Three of this requirement is give synergetic effect for the improve the electrochemical performance of battery. So for hard carbon is known as solid form of carbon that cannot be converted to graphite by heat treatment even at temperature as high as 3,100 Celsius. Or we call this hard carbon with char or charcoal or non-graphitizing carbon. So maybe it just have a porous structure but low degree of graphitization. So I can say that which one is better, porous graphitic carbon or hard carbon? I can say graphitic carbon because porous graphitic carbon has a high specific surface area porous and also high degree of graphitization. And for second question, amorphous carbon, we know amorphous carbon is a non-crystalline phase of carbon and lack of lattice periodicity or non-ordered structure. To transform or to graphitize this amorphous carbon without catalyst, it's need to super high temperature due to a phase transformation typically require extreme external force to break the chemical bonds before rearrangement of the atom into crystalline form as the material undergoes and transition from a thermodynamic less stable state to more stable one. On the other hand, graphitization with presence of metal catalyst could cut the activation energy of transition from amorphous to graphite structure. Or we can say the reaction barrier for this transformation is reduced by the presence of the metal, and therefore the required temperature to initiate the conversion is lower. Maybe this is my answer, Dr. Andri. Hopefully it's enough.
Yes, okay. Thank you, Ms. Fredina, for the nice answer for all of the question. That I believe that the structures will affect to the properties, and also some mechanism is related to the catalytic graphitization, so we could reduce the order to prepare the graphitic carbons. Okay, thank you, Ms. Fredina. Okay. Probably the last section for the question might be for Dr. Su. There's some question, maybe including for my question, because interest with the hydrogels. And again, I would like to say thanks for joining us. If we see the participant, almost 70 people joined today across the Indonesian. So, okay, the first question from the Islamic State University in West Java, Bandung, Win Bandung. If not wrong, the NATO that you present in your presentation made from soybean.
Yes.
And probably he just curious, can soybean used as an ingredient as a polyglutamic acid before become a NATO? So what's the difference? If so.
Okay. So actually, the glutamic acid. Actually, first, glutamic acid is one kind of the peptide in the body. So polyglutamic acid actually is a very biocompatible in body, and this kind of the glutamic acid actually it can be biosynthesized by the bacteria. So we cannot actually we cannot obtain the glutamic from the soybean, but when the soybean is fermented by the bacterial natto bacterial, it will become some like the very sticky things. Actually, the this PGA polyglutamic acid is from the very sticky compound. Yes, the sticky thing in the natto. So actually, it's not from the soybean; it's from the bacterial. So maybe this kind of the PGA have to actually it have to obtained during the fermented of the soybean, yes, by the natto bacteria, yes. And also now we already can synthesize by just synthesize the glutamic acid, the polymerization of the glutamic acid. But if we want to obtain from the bio-based polymer, maybe the soybean can be fermented by the bacterial natto. Yes.
Okay. Yeah. Okay. We understand. Okay. It's very nice. And the second question is from the Haryanto, and the question is, what is the most effective method to produce hydrogel from biopolymers?
Yes, actually, it's a very good question. It's before actually I think about to design a photopolymerization hydrogel, but actually it's depend on what kind of the application you want to use, because I want to use this hydrogel to the tissue engineering. So if I using a photopolymerization of the hydrogel, maybe the UV or when I gelation the hydrogel using the UV, and the tissue is also can be damaged by the UV. So I think UV is not very good for the tissue engineering. So I choose the temperature. So the first part of my presentation is temperature responsive hydrogel. So it can be, we can control the temperature, the gelation temperature during the body temperature, so it can be changes from solution to the hydrogel at 37 degrees Celsius. And actually, after I came to the Uyama laboratory, I know that because as the second part of I introduced the enzyme reaction. Actually, the phenol enzyme reaction is developed by Professor Uyama. So I want to use this kind of the enzyme reaction to the human body, and we found that actually the enzyme reaction is very fast, even faster than the temperature response hydrogel. So it can be gelation very at maybe one second or 2 seconds. So actually this enzyme reaction, I think is very useful to the tissue regeneration. But actually there has a problem because we use the HRP. It has some, it is a kind of the enzyme, but I am not, I think it can be used into the human body, but maybe I'm not sure if maybe someone will have the allergen of the HRP or not. Yes. So maybe we can find another enzyme or something, and then to can be applied to the human body. Yes.
Okay, thank you for the
Yes.
answer. And maybe one question that I curious. I see your
Yes.
presentation
Yes.
about probably about the rheology data, about the storage
Yes.
modulus and then the loss modulus, right?
Yes.
And
Yes.
then how important is the rheology properties in terms of the developing of the hydrogels? Why we have to analyze the loss modulus, storage modulus for our hydrogels?
Yes, because as I mentioned in the introduction, because hydrogel actually, because I want to use into the tissue engineering, and different tissues have the different storage modulus of the hydrogel, like maybe bone is have the storage modulus of maybe 100,000, and if the brain may be only 100 or something. So it depends on the which part of the tissue regeneration you want to use. So if you want to regenerate the heart or the soft tissue of the soft tissue, you want to use as a soft tissue regeneration, maybe you have to choose the very soft hydrogel. So at that time, the storage modules were very important, because if the hydrogel is too hard, maybe the soft tissue, the cell cannot be attached or cannot be growth in the hard hydrogels. And also, if you want to maybe regenerate the bone tissue or something, if the hydrogel is too soft, maybe it cannot be form very good bone cells, and very hard bone to combine with the damaged part. So I think because yes, the storage modules is a good method to first to check the storage modules of the hydrogel, and then to think about what part of the tissue you want to use. Yes, you want to regenerate. Yes.
Okay, yes, I understand. Okay. Again, thank you for the answers, and then thank you for joining us for our today's webinar. And I think all of the presenters have present their nice research and current work that we could learn something for our research. And that's all for our presentation and question and answer sections. Mr. Andi.
Okay, thank you, Dr. Andri. Actually, I have a little words for Dr. Yu issue about the Michel type. Why it's
Yes.
sunflower, not the other flowers?
Yes, because actually I just think that the because the dipropylimer is corona type.
Okay.
So
Corona
yes,
type.
so it's just a sound corona, and then because the triprocopolymer is a flower type, so I just named the mix the dipropylimer mixed with the triprocopolymer is a sunflower. Yes. Yes.
Okay, that's interesting.
Yes.
Okay, ladies and gentlemen, we finally arrived at the end to this webinar. On behalf of Research Center for Physics, Indonesian Institute of Sciences, we would like to thank you once again to all respectable speakers, Dr. Yu Ishu, Ibu Fredina Destyorini, and Bapak Muhammad Ghozali. And also thank you to our moderator, Dr. Andri Hardiansa. And special gratitude to our collaborator, Professor Hiroshi Uyama, Divisions of Applied Chemistry, Graduate School of Engineering, Osaka University. We wish you always in good health. And we also like to say thank you to all our super participants who attended this event and actively participating to this webinar with your questions. We hope this webinar on bio-based polymer and its applications bring mutual benefits for all of us and extend our knowledge and strengthen our research collaborations. At last, we would like to apologize for any inconvenient matters before and during this webinar. Thank you. See you again. Stay safe and have a good evening. Thank you all.
Thank you, Mr.
Thank
Andri.
you.
Thank you, Dr.
you.
Andri. Thank you, Dr. Shu.
Thank you. Thank you.
Our regards to Professor Hiroshi Uyama, please.
Ah, he's not here.
Okay, maybe I will leave the event, or Pak Andri, would you like to close or something?
Yeah, I think that's all for our event today. Thank you for all of the participants, almost 70 probably students and professor from the university in Indonesia join us. And it's a good opportunity to learn something from Dr. Su from Osaka University. Hope we can have another webinar probably next year in another event.
Yes.
Yeah.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you. Goodbye, Su Sensei.
Bye bye.
Thank you.
Maybe
Bye-bye.
see you. See you next year. See you next
See
year.
you.
Hope,
Happy New Year.
hope I can
Yes.
see you next year.
See
Yes,
you.
in Osaka. Yes.
Yeah.
Yes.
See you.
Okay. Bye bye.
Bye-bye.